I'm Sergey. This is Julian, who did most of the work. And what we're going to talk about is something that fascinated me for quite a long time. There is this enormous amount of ingenuity in what people have done with the x86 virtual memory system, and generally with 86 traps. And we advertise this as a history retrospective, and that it will be. We're going to use our famous examples that are just so neat and nifty. They deserve to be universally known as firsts in their area. But we are also going to talk about our own tribute to this, which is how to run computation without ever dispatching an instruction. Life on the edge of the double fault, so to say. And PFLA, page fault liberation arm. PFLA is actually the is a standard acronym for the faulting linear address. And I saw the PFLA, and I had the title for the talk. What we're going to do is I'm going to lead in and then hand it over to Julian. But for a very short, high-level summary, when you look at when you take a computer science class, you are taught about process address space separation and virtual memory, and somewhere there are page tables, and then it sort of stops because no one really ventures into how the x86 really works in your typical teaching environment, because, well, it's hairy and there are a lot more bits there than you can shake a stick at or a page fault at. And but you're sort of left with this impression that, yeah, there are some tables and there is some black magic, and, well, no. It's not just a bunch of tables, and it's not just a bunch of lookups. In fact, the logic involved in there has loops and branches that can be aligned to give you actual full Turing machine power. So that's what we're going to show. And what we owe this to is the people who have explored various pieces of this for some very high-level architectural goals for their systems. We're going to refer to PAX quite a number of times. PAX is a wonderful kernel hardening patch that was a first in so many things. We're going to refer to OpenWall, to OllyBone, and some other projects. So traps are really important. And again, it's not something that people think of as being a part of their program, but they could be, because they live in the same space as your program. They can, in fact, access just about everything your program has to show to the OS. And traps are interesting in the way that there is this hardware layer, and then there's a software layer, and the data that you can write with software, and then the bits of logic that you can't possibly change. And if you look at how the logic goes, it kind of weaves between those layers. Okay, this piece of silicon, or more likely microcode, most definitely microcode these days, it looks into this table. Well, where is this table? Well, this table is actually cached somewhere. That particular entry is in yet another hidden register in the processor that actually implements the translation look-aside buffer, something like that. And so you see a lot of state, a lot of bits that you can set and control by having certain memory actions taken, and you see a lot of transitions. And when I said states and transitions, well, I've described a finite automaton. Now, it's not the end of the story, because in order to build a Turing machine, you need the tape, something which we otherwise know as RAM. Memory. It's not RAM, it's not randomly accessible. You have to scroll back and forth, and if you want to do a standard Turing machine proof. But we can do that too, it turns out, because when a fault occurs, yes, oh, actually, could you skip to another one? Yes. So when a fault occurs, the page faulting linear address and some other things are written to the stack. Well, and you ask yourself, so now stack is a total imaginary abstraction, right? It's getting written to memory somewhere. So one range in memory, the page tables, determines when the page faulting machinery kicks in, and when it kicks in, it writes some data somewhere else, right, on the stack where it's picked up by the page fault, by the actual handler. And Julian is going to walk you through that in the main talk. But how about this? How about we take wherever that data is supposed to go and put it back in what controls our trapping, that is to say, the page tables. And so we can bounce it, and that will happen, right? We are encountering the beast called the double fault, when you can't quite write to the memory properly if that memory is unmapped. I mean, we're writing to a memory address. Oops, we need to translate the memory address. Does it translate? Yes, no. And so we can actually bounce in and out of pieces of different logic if we can write back on the data that controls the faulting mechanism. And that's what we're going to show. Julian's going to show you how to do that. So if you could actually go back twice, yes. And in building that machine, we're going to see a whole lot of brilliant engineering ideas that people have had over years looking at the memory system. And you know, there is return-oriented programming and return-oriented programming without returns, and you know, for every kind of an instruction there is that kind of instruction-oriented programming these days. So why not make another term? I call it trap-based design patterns, or trap-oriented programming, if you will. And if you look at quite a number of projects such as PAX and OpenWall and OllyBone and Plex 86 and other systems, ShadowWalker among them, you will see that there are consistent engineering patterns. There are consistent tricks that people have used. For example, what is the most overloaded part of your operating system if you're looking at kernel hardening, policy enforcement? Why? It's the page fault handler. You set certain page and table entries to trap for accesses that you don't want, and then you determine in the page fault handler whether this is a good fault or a bad fault. And this is how PAX does quite a number of things that it does, and this is how OpenWall does its kernel hardening as well, and quite a number of other systems. Then you ask yourself, reads and writes. Can we to a page? That's a really poor, small set of things that you can trap on. Can we do better? And in fact, people have combined arming several bits across the page table entries, and we're going to look at those data structures, and got combined events to trap. OllyBone, for example, trapped on fetch from a page just written. Think about it. If you want to catch an unpacker, what does an unpacker do? Writes some code, then jumps to it. You want to trap on that, not on, you know, any write or any read or any fetch, and you can do that. There are really bad data flows through which kernel exploitation happens. You know, you massage this crafted argument to a system call in user memory, and then you call the system call and you have the privilege elevation. next thing you know. You want to reduce such flows. But then, of course, you want to allow the right kind of flows. And what you want is to be able to label memory according to how it's supposed to be used. And again, you look at a number of projects and you find that they manage to craft those labels across the different trapping bits. Isn't that nifty? And a thing that totally blows my mind is that you can also store extra state in the TLB. So before Intel and AMD added the non-executable bit, and you could start, you stopped being able to jump right into that trivial stack buffer overflow payload shellcode. People have emulated non-executable bits. People have caused memory translation to trap when jump went to tables to pages that were supposed to contain only data. And they did so by using the fact that x86 has two different translation look-aside buffers, one for data, one for code fetches. And again, we're going to get to that. If I can do some hack like that, I consider my career topped. And of course, you have hacker debuggers. Hackers have been the primary provider, the primary purveyors of creative debugging. So a breakpoint is a special instruction. You know, int 3, int 1, whatever. But in fact, you can trap into any instruction that causes a trap, such as an illegal opcode or some sort of a floating point condition. And if you can catch that, then you can base your debugger on something that's completely not an intended breakpoint, but it is, because all traps, all faults are created equal in that respect, if you can hook them. And so, say the Rust debugger, the thing that was used to reverse engineer Skype, got around Skype snooping in memory. Is there a debugger there? Does it look like int 1, int 3 are armed? If yes, then we'll just jump to this page of crappy code and loop there forever, confusing the reverse engineer. So they got around that because they used traps in an unorthodox way. And there's just so much stuff there. Eventually we'll come up with a paper. And it will be the nearly complete paper because, of course, a complete story is only written by the entire community. But what we're going to do now is to go through all of these great examples and then build up to a full Turing machine, showing just how much power that thing has. And I'll turn it over to Julian.
Okay, thank you, Sergey. And because before we can assemble a Turing machine out of all of these nifty things that wound up in the Intel process over the years, you need to understand them. I'm going to give a quick primer on the various components I'm going to use to assemble my own-ish sauce. And because I don't want to be yet another boring lecture, I'll do this based on all the cool hacks that Sergey just mentioned and try to explain how they work as we go and as I explain the various mechanisms that Intel has used to implement virtual memory. The original point of virtual memory is that programmers like if things are really neat and orderly. They would like to have a flat 4 GB address space, even if this is in the middle of 1980, and even the richest kids can only afford 2 megabytes in their computers. And they would also like, even if something has to be paged out or a page has not yet been allocated yet, they would like to pretend that it's in fact there. The actual underlying hardware looks something like this. It's full of legacy, has a few cracks in there, and some pages might not be there, some pages might be quite dirty. Others you'll just have to fetch from the architectural dig site where they might be stored. And the first mechanism Intel tried to do back in the days of the 286, when most people were writing 16-bit DOS code to create this illusion of virtual memory, was the segmentation mechanism. No one ever really used the segmentation mechanism on its own. OS2 did for a while, really ancient versions of Windows maybe. But it was very quickly, in the next generation of processors in the 386, replaced by the paging mechanism. But it still is in there. Even the most modern Core i3 processor you can buy from Intel still contains all of these features. And Intel's spending a lot of effort in making sure that they work exactly as they were working back in the original 286, so you can still run the same code. Segments are basically typed regions of memory. You say, hey, I have a block of memory that starts here and that's that long. And then you can translate a logical address that is a selector. Hey, this is going to be the code segment, this is going to be the stack segment, this is going to be data, and 3 other ones that you can use, and then offset into that segment into a linear address. It just has a register that stores the base and the limit, and that allows you to add some typing information to memory, and also to make multiple such segments that might not overlap, coexist in memory so as to separate processes. This has a few rather nasty downsides. This has a few downsides, namely that a segment needs to be continuous in physical memory, and everyone who's at any point written a memory allocator knows that if you try to allocate various things of different sizes, you're going to have very inefficient memory use. And if you only have 2 megabytes of memory in the first place, and you try to implement this mechanism to make better use of it, it better not have too much overhead. And those segments are stored in 2 descriptor tables called the global descriptor table, GDT, and the local descriptor table, which are just tables that, in a very weird and legacy-compatible encoding, contain the base and limit addresses. As I mentioned before, this mechanism was nearly never used. Almost all segments had their base set to 0 and their limit set to 4 GB, so the segmentation translation mechanism never did anything. But hackers have always kind of kept it in mind, and one of the first teams to use this was the OpenWall team, who maintained a Linux kernel hardening patch. And they wanted to somehow prevent the really basic smashing the stack for fun and profit attack that you could read about in Frack, if you go really far back in the archives. They just changed this code segment that is used to fetch instructions and changed its limit to 3 GB minus 8 megabytes. Under the assumption that the stack would live in those 8 megabytes. So as soon as the CPU tries to execute an instruction from the stack, they would trap. Because there are some things that actually execute instructions from the stack, for example, GCC can create those trampolines, because GCC is a piece of shit, sorry. They actually had to go in and decode the instructions that caused this fault, see, okay, is this GCC being stupid, or is this someone owning my box? If it's GCC being stupid, they'll let it pass through. If they detect a very specific condition that someone is returning to the stack and it's not a GCC trampoline, then they kill the process and hope that someone will debug it if in fact they made a mistake in decoding GCC. And the other mechanism that people use instead of desegmentation to provide virtual memory is the page table system. I'm just going to present a simplified view here on how it was before the Pentium, while you could only have 4 GB of physical memory, but the same basic principles still apply. You take the virtual address that you want to fetch, that might be an instruction or that might be a piece of data that you're just loading with your move, and you split it up into 3 parts. You take the first 10 bits, you take the second 10 bits, and you take the last 12 bits. There is a special register in the CPU called the CR3 register, and that points to a page in memory that is just full of such table entries. And in this case, our first 10 bits are going to be hex 37A, so you add 37A to the value of CR3, and then you get one of those structures in here. These contain a pointer to another page. Sorry if I spoiled the joke. These contain a pointer to a page table, to which you add the second 10 bits in the instruction, thereby giving you a descriptor of a single page of virtual memory. And that contains the address of the page frame in physical memory where you'll actually fetch from. This is slightly simplified. In modern processors with 64-bit, you don't have those 2 levels of indirection. You in fact have 4. But the same principles still apply. Added on top of that, they have a few rules that need to hold for this translation to succeed. For example, the last bit in each of these descriptors is the present bit. That just shows, okay, this is in fact a valid translation. If any of these present bits is not cleared, the processor stops walking these tables and causes an interrupt. There also is a bit, the user bit. If you're in ring 3, that is, if you're a user space program, this user bit better be set when you're trying to access something. That's how you protect someone from overwriting kernel data structures. And there's also a write enable bit that needs to be set if you want to write to this memory. That's how you can safely share code between different processes and implement things like copy and write. And what happens if, for whatever reason, one of those constraints is violated? Well, you get a trap. But traps tend to happen quite often, actually. Even your regular operating system textbook will mention all of the uses for trapping. For example, things like demand allocation and swapping and memory mapping are all implemented with trapping in the end. They're all somewhere off the page fault handler. Usually work by setting either the right bit, or by clearing either the present or the right bit somewhere. Hackers have also looked at this mechanism and have found, as Sergey has already mentioned, a whole bunch of really cool uses for it that sometimes don't come just from the intended behavior, but also from implementation artifacts. Because as I mentioned, modern processes, for example, tend to have 4 layers of indirection. So every time you want to read a virtual address, you first have to perform 4 memory accesses to look up the page tables, and then another access to actually get the piece of memory that you want to access. Well, if you want to do 5 memory accesses per actual virtual memory access, you're going to have an issue because memory is already much slower than the CPU. Therefore, the page tables themselves might be the nice abstraction that are in the textbooks, but what actually drives the translation mechanism is a special buffer for that called the transaction look-aside, or the translation look-aside buffer, TLB. And the TLB is just indexed by the virtual address and contains the page frame number that this virtual page gets translated to, as well as these permission bits. And because this TLB is actually so important to driving it and gets accessed all the time, it's one of the most performance critical features of the CPU. In order to not have any contention around this, they actually have 2 separate TLBs since the Pentium, so very quickly after they even introduced this mechanism. One that handles translations for instructions and one that handles translations for data accesses, because these happen at different parts of the chip. And that was used by the PAX project to actually do a couple of cool things. PAX is also a general catch-all hardening patch for Linux kernel that tries to, and is very good at actually making it a lot harder to exploit the Linux kernel and applications running under it. And they also wanted to break smashing the stack for fun and profit, without just restricting themselves to catching that one very specific condition that OpenWall could hit. And a bunch of other architectures have mechanisms that allow you to prevent code from being executed from one page. Nowadays it's known as the NX bit, or data execution prevention, and we've all had it since about 2005 because that's when Intel made it on their CPUs. But these the PAX team wanted to actually develop this about 5 years before Intel added it to their processors by cleverly using these implementation artifacts. They actually have 2 separate mechanisms of emulating that MX bit. The first one uses the old segmentation, just as OpenWall uses it. They do it by splitting the virtual address space in half. The lower half is going to be reserved for data, the upper half for code. They just point all the segment selectors to the lower half and set the limit to 1.5 gigabytes, except for the code segment, which is going to be just in the upper half. Because the segmentation mechanism adds the base at every point, the instruction pointers are just going to work just fine as long as they remain below 1.5 gigabytes. And then you can use the paging mechanism to not map the instructions that you don't want to be, not map the pages of memory that you don't want to be executed from in the upper half, and the ones that you don't want to write to, you just map them read-only in the lower half. The issue with that is that on certain issue bit, the instruction space is already, or the virtual address space is already very contended, and you have, if you have a big database server, you might want to access more than 1.5 gigabytes of RAM. And also in modern processes, the segmentation feature, because no one ever really bothered using it, is very much de-optimized. And especially in performance critical code, that can be a sizable overhead. Thereby, they looked at other mechanisms in how they could potentially achieve the same result of emulating an X bit even though their processors don't support it. And they knew it would take Intel quite a while to actually implement it. And this is Sergey's favorite little trick, so I'm going to let him take over again for 2 slides.
So there are 2 things that your machine does, your processor does, when it sits in that fetch, decode, execute loop, right? It fetches instructions, or it fetches data. And it just so happens that fetching instructions happens quite differently. There is the pipeline, and you're not just fetching one instruction, you're fetching a whole bunch, and you're putting them through the pipeline, and you might even have so-called speculative execution, trying to execute instructions that are not yet under your instruction pointer, but will be, hopefully, and then maybe you'll roll back if you don't reach them. Long story short, there are 2 paths in x86 processor, 2 different paths in silicon and 2 different bits of microcode logic. And one is for fetching instructions, the other is for fetching data. Accordingly, since every address has to go first to the segment translation, then through the virtual memory translation, there are separate caches that make those translations fast, because any instruction that you issue has a virtual address or a linear address and a virtual address. So you have those translation look-aside buffers where you cache the instructions of your page table lookups. So you have the same set of page tables, 1 set of page tables per process, but 2 caches, ITLB and DTLB, instruction and data. And remember our page table entries, they have the supervisor bit. Okay, a user supervisor bit. Now, if it's cleared, and you're not in kernel mode, then in ring 0, then you trap. The page fault handler kicks in. And then you can see if you are accessing the data page, depending on where your instruction pointer is, or not. And that's the theory. Let's see how they implemented that in practice. So what they did, and this is absolutely brilliant, they took the page table entry and cleared and set the supervisor bit. So there is a trap when you try to access that page. Page fault handler kicks in. Checks if where your instruction pointer is, and if it's in this page and this page is data, then clearly you've just tried to execute data. That's too bad. You can no longer trust the process. Of course, there could be other reasons for the page fault, such as just the address was bad, or you need to allocate more stack if you're within the stack area, and so on and so forth. But then, if that's a normal data fetch, this is what you do. You want to let it go through. You could, of course, just set the present bit or the supervisor bit on every data page and trap every time on every access. And that would kill your performance. That would kill your performance dead. Instead, you run one instruction with the corrected bit. You let the data access succeed. That populates the DTLB. So the DTLB has the non-trapping setting of the supervisor bit. Then you immediately change back the page table entry to trap again. So now, if the access comes through the page table, it will trap again. But if it comes through the data TLB, DTLB, and that does it all the time, you know, cache misses, you know, your TLB misses are rare if you work with the same set of pages. This is the primary mode of operation. Then it will sail right through. But if it's an instruction fetch, remember, that entry is not in the ITLB. So when the instruction fetch would come through to that address, it will trap on that page table. The right entry is only in the DTLB, and it's desynchronized in the setting of that bit from the actual page table. Isn't this absolutely nifty? You know, there is this extra bit of state that you manage to shove into DTLB, and now you can emulate the non-executable bit. This is beautiful because it reflects the intended use of memory. That's old school labeling. That's how a system should be built. So OllyBone uses a similar technique. Why don't you take that, Julian?
Okay. OllyBone, when a lot of times when people write malware, they don't like it when other people look at that malware and analyze it, because they want to spend a lot of work and they don't want it to be immediately reverse engineered. And so to reverse engineer such packers is usually a lot of hard work. And then someone goes along, changes the packer slightly, and you have to start all over again. And the people who wrote, or the OllyBone team thought, hey, we can fix that maybe. You know, we could also just wait, or we could load it up in a virtual machine, look at the unpacked malware, and then just load it up in it and attach a debugger at runtime. The issue with that is then you get the program or the malware somewhere in the middle of execution, and you might have lost some state. It might already have clobbered its initialization code, or it might have multiple stages of polymorphism or something. And so instead I said, wouldn't it be cool if we could figure out first, and stop execution right after it's done unpacking and just before it executes the first instruction of the packed binary? So they want a trap condition that they want to get the debugger, in this case it was OllyDebug, to stop the first time someone executes from a given page after they've written to it. So you just, every time the code changes, the debugger stops precisely once, and you can look at it, and you can dump that, and then you can continue execution so you don't have to manually step through the entire unpacking process again until you grow old and tired of it. And to do that, they used exactly the same technique as packs, to first trap when you write to it, and then keep that in the DTLB, but trap as soon as you jump to the execution of it.
So by now you're starting to get the idea. You can program with those bits. They're not just page table bits, they're memory. They're memory that you could stick pieces of state into, just like variables.
And so far, all of the hacks we've seen are relatively tame. I mean, these two have just messed with one single bit. They've used the user and supervisor and the read-write bit. However, the page table contained the much more juicy bits, namely where the instruction is, or where the address is actually translated to, what page frame number we have. And that was used by a rootkit called ShadowWalker, because wouldn't it be nifty that if, say, the good neighbor Goodspeed here had installed a rootkit on your machine and you were to debug it, you would still be seeing your whatever hardened Linux patch you have on there, but when the CPU gets around, it realizes it's Spargelzeit and therefore decides to execute whatever nasty OS code you've loaded. They use the same trick to trap whenever you have an instruction fetch, to quickly change, or whenever you have a data fetch, to quickly change what page frame number it points to, so you have the unpatched OS code, but actually make sure that the ITLB would see the whatever patched OS code you might have. They were creating a rootkit that is rather nasty to detect. And the same trick has also been used by packs to detect implicit flows from user space to kernel. So usually if you have some sort of privilege escalation vulnerability or find a buffer overflow in the kernel, you want to get the kernel suddenly starts accessing code or data in user space in places where it shouldn't normally. The interface between the user and the kernel is rather restricted, and in Linux there's actually a bunch of macros that determine this very well. And so packs used the same TLB synchronization tricks in newer versions of packs to detect when the kernel starts to access user space, code and data that it shouldn't ever access. And they also used a few GCC plugins to find the spots in the kernel where the kernel is actually supposed to access the user space.
And it's, I absolutely I absolutely recommend that you see the Hackers to Hackers 2012 presentations by the PAX team. For quite a while, they have not been giving hacker conference talks, which is a great pity because that project just embodies the spirit of engineering with the bits that chip manufacturers forgot and building something beautiful out of them. What they have there, and they're starting to use the new features such as SMEP, supervisor mode execution bits, and SMAP, supervisor mode access traps, to prevent the kernel getting the data that it's not supposed to be getting. It's the implicit flows that drive your typical exploitation. Pieces of data making it into pieces of code that are not supposed to be working on them. And if you can trap that, then you've essentially blocked that route for exploitation. What you see is beautiful labels that allow you to mitigate those data flows that are spread across those bits. So again, this is more like programming. This is using those bits, changing them on the fly. They're not static. They represent the view of the process that is currently the kernel and the data and then the userland pieces are supposed to have. This is a dynamic way of denying those flows by presenting the right set of page tables. And I absolutely implore you to go see that talk. It's a wonderful introduction into the complexities of x86.
And so I saw all of these truly amazing things you could do with the virtual memory system. And I thought, just how far could we push this? And then I had a dream. I had a dream of a world where you're no longer judged by whether you have a white hat or a black hat or a straw hat, but rather by how weird precisely your machine is. I had a dream of a world where you no longer believed what the textbooks say your processor does, but you actually take a look and experiment around. And I also had a dream of a world where a small step for a debugger can be a huge step and in fact change your entire world without anyone ever noticing, as things go. And I managed to build a mechanism by which we can have an arbitrary program running inside just your MMU, using these trapping features and the translation features. So you write a program in this. It has some restrictions on what memory it can access, but it can perform any computation you want it to do. Someone loads it up in a virtual machine. As I'll point out later, the actual virtual machines out there crash. Intel claims they have a super secret VM that they're not sharing with anyone that should actually be able to emulate this correctly. If they do and they load it up in there, they can single set the instructions. They'll see that no instruction ever finishes executing. So theoretically, nothing is supposed to happen, right? It just looks up these tables and it never finds anything. Boring life. Except in the meantime, you have sweet, sweet Ode sauce dropping from your processor. And now I'm going to quickly go over the various components used to build these things together. The main primitive we have is the hardware task switching mechanism. Back in the old days of DOS, of yore, when people wanted to first write multitasking operating systems for these pesky little PC processors that everyone had, everyone did their own task switching, and most of the people did it somehow wrong. And Intel came along and saw we could help them. We could have a single instruction that stores the end, or we could have a single mechanism that stores all of the CPU's state atomically somewhere in memory and loads it from somewhere else. Context switch in just one instruction, without having all that nasty assembly that is in every operating system. And we use that to completely change the CPU's worldview from an interrupt handler without having to write any instructions. Then, as we mentioned before, the page fault handler is supposed to look somewhat like a regular function, so it takes parameters on the stack. We use that act of pushing down the stack as our arithmetic, So every time we execute an instruction, you decrement the stack pointer by 4. And it turns out if you can no longer do that, if the stack were to underflow, that creates a double fault. And with that double fault, that means we can now jump somewhere else. If we don't have a double fault, we just point our instruction handler to invalid memory, leading to just yet another page fault. So the faults just keep looping and looping and looping. Nothing is ever supposed to happen, except things do happen. And to understand that mechanism, you have to do how precisely you invoke that interrupt handler. So far we've said, yeah, you have these tables, and then you wind up in the interrupt handler. You have user space program, then you wind up in C code. Hand-wavy magic in between. But if you actually blow away the smoke, you realize that these traps, which are normally not considered a part of your regular program, unless you happen to be the one guy who's writing low-level OS interface code, do have that computational power that you want to use. They have internal state, and they are also controlled from system RAM. So they're just like assembly instructions in your program, except infinitely more weird and completely not understood by anyone who wants to reverse your code. In a typical interrupt, there are various cases on what exactly gets pushed to the stack. Almost all exceptions push the error code to the very bottom, and below that you might get other parameters like where the exaction happened, and if you switched stacks, what the old stack was. There is the usual Intel interrupt handling mechanism, which operating systems nowadays use, which I'm going to skip because we're slowly starting to run out of time, and go immediately to the task switching mechanism that is used nowadays exclusively used to recover from the OS after a hardware fault or a weird OS bug has completely corrupted your state. That's the last thing you see before your Windows machine blue screens. That's the only thing it does. And on Linux, you immediately get a kernel panic. This is this task switching mechanism which can reload the entire CPU state from a segment. This goes back to the old 286 days. So they have 2 layers of indirection. In the interrupt descriptor table, which shows where the interrupts live, you have this descriptor. This has an offset here into the global descriptor table, which contains a bit of metadata and a few flags, and also the address in memory where the entire CPU state is actually going to be stored. And that's this nice massive structure, which contains everything the CPU was supposed to have in the days of a 386. And also down here for the regular interrupt handling mechanism has a whole bunch of stack pointers, one for each ring of the CPU protection mechanism. Usually you only use the operating system one and the user space stack. And the way the Intel manual says this task switch works is first, you see, okay, I'm going to switch to a new context. So I need to save the current context I'm in. It stores all of these registers into the memory. Then it does this 2-layer indirected lookup. Then performs actually, they wanted to prevent you from looping these faults, as I'm going to do, because they anticipated something nasty was going to happen. So they added a flag that says, is this task currently busy? If yes, don't switch to it. So we need to check that this busy flag is cleared and that all of the segments that are in there appear to make sense. Then it loads all of the new state atomically. At this point, it can no longer return. Whatever happens thereafter happens in the new tasks. If there's another fault, it needs to finish this task switch as much as possible and then resume the error handling thereafter. That's how we can chain the faults together. And then it pushes the error code. If it can't do that, it dispatches a double fault immediately afterwards and doesn't change the stack pointer. If not, it goes to a new EIP. I'll give a very brief 1-minute digression here. The Intel manual says, hey, please don't put this TSS on page boundaries, because this is supposed to happen as an atomic operation. We're just looking up the first byte of this, where it is in physical memory, and then read the entire 104 bytes continuously from there. And I thought, hey, there's this thing called a virtual machine, where pages from different operating systems get thrown together. And I can set up the task switching mechanism, so I could set it up that one of these task state segments, or TSS, are at the very end of a page, and then I can read the 103 bytes of the page after that. And if that happens to be, say, the code of my hypervisor, I just own Amazon EC2. And I was about to prepare to do the O-Day dance, and was very, very happy that Intel provided this in their manuals. People do read them, sorry. and was like, yeah, here'll be dragons. Until good neighbors reminded me that we're scientists and we try things out before we do the O-Day dance. It turns out the Intel manual is slightly wrong here, and they actually translate double word by double word, which appears to be a lot more boring, but people familiar with Sergey's previous work know that manuals can be quite cool in their own, and that double word by double word translation actually allows us to perform arbitrary computation, which may not be as immediately as great as owning EC2 and being able to break out of a virtual machine, but it's still quite nifty. And we have our 3 parts of the instruction. Well, if we can chain faults immediately after one another, and it decrements the stack pointer every time. And if the stack pointer happens to be less than 4, we take a double fault. If not, we just immediately go back to taking the next page fault, because the page fault handler isn't in valid memory. So we have and this actually turns out to be enough to write any program you want. This single weird assembly instruction construct is enough to implement is just as powerful as your regular CPU, even though the programs are going to be much worse to write. There are academic papers on this. They cost $200. Wikipedia also, for once, explains it rather well, so you can just look it up there. And in detail, we get this instruction. It has a move, so it moves from X to Y. If the value we moved was less than 4, we branch to location B. If not, we decrement it by 4 and branch to location A. These variables are going to be the stack pointers in individual task state segments that is split across a page boundary, so we can share the same variable between different tasks. And the global descriptor table that shows where all of these segments are is going to be the same across all tasks, but we have a different interrupt descriptor table for every task. You're not supposed to switch these, but because all of these things go back to the 286, they live in the address space produced by segmentation, and are actually in virtual memory. And with the task switching mechanism, we can switch out the page tables. Therefore, even though the interrupt descriptor table is supposed to be the same, and has the same virtual address, we can change the meaning of this virtual address arbitrarily often, and can just point it to a different instruction every time. And the branch not taken jump will be a page fault, and the other one a double fault. And the upper half of the TSS does correspond to a variable, and we map the values that we want to be loaded by the next instructions, that is the Y, the source of the move, for the next 2 instructions in the spot where they're supposed to be, and map the destination of our current instruction in the task where our instruction lives. Thereby, as soon as we have a fault, the CPU will see, oh, okay, I'm going to load that entire task state of the branch we take. This loads the source operand. Then it performs the task switch when it gets new page tables, and then when it saves that state, again, back to ostensibly the same virtual address, it actually winds up in a completely different place in physical memory, giving us our move. This sounds very nice on paper, and I had this figured out relatively quickly, but then real life struck back again, just as we didn't get our O-Day. Because there's this one stupid bit in here. All of this mechanism took about a week to design, and this one bit took me about 9 weeks. If you could find a person at Intel who is responsible for this bit, I'll buy him a beer or punch him. I'll have to think about it. And I worked around various schemes on how to get it, and the way I eventually worked around it is by mapping the lower half of that TSS onto the GDT, and duplicating the entries that are supposed to be in a GDT into general purpose registers, EAX and ECX. So in every task state, it just says, okay, I'm going to save my current state back, and thereby actually overwrites the GDT. So if things align just right, that busy bit always gets cleared. The issue with that is that the GDT is only 16 pages long, and therefore we can only use the entries in the GDT that are in the global descriptor table that are at the very end of a page. So we only have 16 possible entries in the GDT. Which also initially sounds like it's going to be ridiculously stupid. Hey, you can only have 16 instructions in here. But with a few tricks, and again using remapping through virtual memory, you can define a few mathematical constraints on your instruction call graph, which turn out to be almost always satisfiable. And you can implement any arbitrary program in there without that restriction. It just makes programming even weirder and occasionally requires a little bit of fidgeting around until your instructions look just right. But it's still Turing complete and you can implement the game of life. And there's, however, still a few unfortunate restrictions that we're largely stuck with. One of them is that we only have our one really weird instruction. And with the physical memory we can write, the only thing we can perform arithmetic with are the stack pointers. So they all have to have a certain alignment with respect to the physical pages. We can only touch the last 32, or we can only touch 4 bytes of every physical page. I originally wanted to implement a game of life that runs on your VGA frame buffer without any instructions being dispatched. Turns out it's rather hard because you can only access 8 pixels. If anyone brought their microscope, I can show them a demo. And of course you need kernel access to set it up in the first place. Which brings us to the second big application of this. The one place where you have kernel access in a hostile environment, the double dose strength red pill. Because no publicly available simulator that I've seen, and I've looked for quite a while, implements this correctly. My favorite is QEMU. They just decide to do it so it passes the unit test. Because, especially the double fault, no one uses the task switching mechanism except for double faults. Double faults only happen on kernel bugs, and who would ever use something like a virtual machine to debug an OS? Box can actually do it rather well, and their code is very nicely documented, and it actually can run my particular weird machine, although I'm sure you can find things where Box breaks down. Symix, which is Intel's internal simulator, that is thankfully accessible for free to academics on the cloud, just reboots the virtual machine. With a few changes, it crashes. The same few changes also cause KVM to kernel panic the host. And there is an academic simulator that I was looking for called PLTSim, which is used quite a bit in research. And the source code for that says, well, here we're starting to log this exception, but during doing that, we're going to corrupt the virtual machine state, but it doesn't matter because we have a double fault anyways and the world is over. Intel views that the world is over after a triple fault, but, well, who needs that accuracy thing? And now as a quick recap of what you can get from it, if you're wearing a white hat, you should learn from it that you should really look at how the individual components you build your machine from work, and what your software can do that you wouldn't think it does, and never ever trust the spec. If you're a black hat, you get a double dose 2,000 milligram red pill to break out of any virtual machine you want, and currently it crashes most of them, but with a little bit of work you could maybe have a branch environment in VMware and completely confuse any reverse engineers. Or you could own whatever forensics lab is messing with your code. And if you're wearing a straw hat, as I would if I hadn't forgotten it, you have a weird machine, and weird machines are cool. And to continue this research, I'm currently working on 64-bit. They cleaned up a lot of the interrupt handling, so I'm pretty sure I can clean up the weird machine. And instead of having an hour talk, I could probably explain it in 5 minutes. And we also figured, if no software emulator can handle this, why should all the different hardware vendors implement it correctly? What happens if you do this on AMD? I don't have an AMD box sitting around, so I didn't run it yet, but I'm going to find one, and I'm going to report what happens. And the code for this, I had to skip the demo, especially because it's, unless you can step through it in a debugger, it's not quite that impressive. We'll be on GitHub in about an hour, and you can follow us on Twitter, where we'll also announce updates. And so, maybe we still have time for a couple of questions.
Yeah, thank you very much for the interesting talk. We're still going to take questions, as usual, from IRC. And we have 2 microphones in the room, one on the left-hand side and one on the middle. So please, if you want to pose a question, please line up behind the micros. Is there anything on IRC? OK. Is there a question from the room?
Doesn't bode well.
OK, not?
Yay. OK.
No questions.
Well, I guess people want to get going to the closing event. I don't know. So, yeah. Oh, I see there's a question on the left-hand side. So please,
hey, last talk of the day. Thank you for sticking it out.
Thanks a lot for paying attention for so long, even if we hurried it up.
I'm quite amazed we retained the audience that we did retain.
So So, but we're still going to take the question, yeah, from left-hand side.
I have what's hopefully a quick question. So what's the best way you've seen to fix this issue in a VM or in the actual machine, or an OS?
Well, in a VM, it's really hard because the mechanism is complicated, and there are many other mechanisms like it. Read the spec really well, and also run your experiments, and maybe run things like this. That's partly why we published it. On a CPU, you can't fix it because it's part of the legacy. When Intel did it with the 64-bit, they removed a lot of this craft.
Well, but of course, for the CPU itself, it's not a problem, strictly speaking. It's the issue that the CPU has to be backward compatible to mechanisms that used to be there since the days of the old Republic. And we're talking about the tagged architectures and the time when segments were really a basis for a strong security model and actually meant something semantically. And it's just too bad that tagged architectures did not make it into commodity computing markets. They are definitely well known to folks like the PAX team who are protecting commodity systems to a fraction of the standard that tagged architectures would give you. So it's hard, and it's hard to emulate a complex system. But what can you do? This is the world we live in. Complexity is, as we say in our other language theoretic talks, complexity is kind of like this dark energy. It doesn't go away.
Thank you.
Okay, are there any other questions in the room or in IRC? Well, if not, so I ask you again for a warm round of applause for our two speakers.